Let's see. Nothing's working. There's nothing working. I just want this guy. All right. We're now moving on to electromagnetic waves. Oops. We've talked about static electricity, and then we talked about static magnetism. Those are electricity and magnetism that don't involve movement or change. And then we talked about how when you change electric fields, in other words, you have moving charges, currents, they're affected by magnetic fields, or they create magnetic fields. When you have changing magnetic fields, they actually affect currents and charges. So there's obviously some connection. And it was a guy named Matt. What was his name? Clerk Maxwell, an English bloke who took a bunch of equations, some of the equations that we've seen so far. There are 4 of them in total that end up being called Maxwell's equations, even though he didn't discover any of them. But he put them all together and solved them. Now, if you've ever seen these equations, you'll know that's no trivial thing. Let's take a look at them. These are Maxwell's equations, right there. This symbol is called the del symbol, and it signifies a full spatial triple derivative. So these are differential equations, and of course you have a derivative in time as well. So solving these equations is extremely challenging. Now it's just a homework problem for physics majors. But back then, it was nothing short of amazing, maybe even miraculous. But he solved them. And when he solved them, he got something really interesting. This is one of the equations that he got right here. And it's obviously, again, not very trivial. It's a very complex thing involving many dimensions. But in the end, what he got was something that looks like this. You have the second derivative of the electric field, is equal to the second derivative of the electric field in time. And he got the same thing in the magnetic field. He got two equations were the same for electricity and magnetism. And you might look at this and say, well, so whoop-de-doo. But this has a lot of meaning to physicists. First of all, if you have a second derivative of a function in space equal to the second derivative of a function in time, that means that this is a traveling wave. So what he discovered is that electromagnetic fields, when you combine electricity and magnetism and they work together, so when they're changing, electricity when it changes creates magnetic fields, and vice versa. When magnetic fields are changing, it creates electric fields. When you have those things going on, it creates waves. So that was the first thing that he discovered by solving these equations. Well, that was already known. Well, it wasn't actually known. It was a scientist back 150 years before Clerk Maxwell in the same country named Thomas Young, who discovered that light was a wave, a traveling wave. So we knew that light was a traveling wave. Now we know that electromagnetic fields are traveling waves. But what we didn't know was the connection between those two. And here is the connection. Mu epsilon. Remember these two constants. We used mu when we did magnetism. We used epsilon when we did electricity. When you multiply these two numbers together, you get the square of the speed of light. Well, not exactly. You get 1 over the square of the speed of light, but that's neither here nor there. No, you get the square of the speed of light. Anyway, you get the speed of light eventually. And this is important because this part of this equation tells you the speed of the wave that this equation is describing. So this should be the square of the speed of the wave, and it turns out it is exactly the speed of light. And so what they discovered at this point was that this is an equation that describes a wave of electricity and magnetism. And the wave that it's describing travels at the speed of light. And as far as we knew to this point, only light can travel the speed of light. And so this was obviously explaining light waves. And that's exactly what made this so amazing, was we discovered what light waves are for the first time. We never knew before this. We never knew what caused light to occur, what caused things to glow, what caused colors to be what they are. Now we knew. Now we know. And we didn't do it by experiment. We didn't do it by measuring anything. We did it by theory. And this was a huge step forward in science. To this point in science, the scientific method was mostly about going out, measuring something, making a guess on what it means, testing that guess by measuring some more. Scientific method like you were taught in biology or chemistry or whatever else, right? You do something, you measure it, you make a guess on what's happening, you measure it again to check that guess. We call those hypotheses. You have a hypothesis, you have data, you have analysis, you compare your results with your hypothesis. Does it prove it right or wrong or otherwise? And then you move on. That's how science was done all the way to this point. And frankly, that's how science is done still in biology and in chemistry and other things. It's how it's done in almost every science except for physics. This method changed the world. It changed everything that we know about technology and science today that is new, came from this idea, where you can take mathematical models, you can take equations that describe what you've seen, and you can take the next step. You can create a model that explains what should happen next, and predict things, and discover things without ever measuring anything. And then you can go and check to see if you're right. It had not been done before. And it had been done before, you could say it had been done before, but in very small ways. And they're making progress towards this over probably 50 to 100 years. But still, this was the first really big one, where somebody just came along and said, you know what? All these equations seem to be related. I'm going to put them together and solve them and see what happens. And not measure anything. I'm just going to solve equations and push the theory beyond the experiment. And it was the beginning of theoretical physics, really, you could think of it as. I mean, it's not necessarily fair to say it's the beginning of theoretical physics, but it was kind of the beginning of mathematical modeling for theoretical physics, where we're using math as our tool to push forward the understanding. But this is how we've done so much today. There are so many things now that we understand mathematically, and we have very few measurements for it, but we take advantage of the mathematics to do great things. So many things. Almost every discovery made in science today that is truly new and truly amazing is done mathematically years before it's ever done experimentally. So this was one of those great aha moments, one of those great, really amazing moments in science, is the discovery that light is a wave of electricity and magnetism. It's a light of electromagnetic fields that are changing. It's a wave of these fields that are propagating through space. And it turns out that they don't have to travel through anything. We learn that later. They can travel through vacuum. But it becomes extremely important to us. Right here, they show this picture of all these fish and these colors. Well, every single thing you see in this picture, every single thing that you see anywhere in your life will always be electromagnetic waves created by the electrons vibrating inside of those things. So the fish that are orange have electrons in their skin, in the molecules in their skin, that are vibrating at a frequency that lets off orange electromagnetic waves. The frequency for orange is right around in the 600 and something nanometer range. That's the length of the wave. The frequency, we don't really talk about light frequencies because the numbers are extremely big. So we don't talk about frequencies when we talk about light. We usually just talk about wavelength because you can say it's this many nanometers, a couple hundred nanometers or whatever. The blues here are probably somewhere in the upper 400 nanometer range. The greens over here are probably in the lower 500 nanometer range. They're different waves with different wavelengths, and they're all electromagnetic waves caused by vibration of electrons. Some of the vibrations of electrons we can't see because our eyes can only see a very small fraction of the electromagnetic waves out there. Not a fraction of a fraction. Extremely small number of waves that we can see. At Kennedy Space Center in Florida, they have this great big radar dish, as you're used to seeing and calling them. These are all over the place. We have some over by the Walmart distribution center. We have some out by the lake. These things are all over the place. And these are detectors that detect much larger waves than our eyes can detect. Our eyes detect things that are in hundreds of nanometers, which is like, a few thousand atoms big. We can detect waves that are about the size of a few thousand atoms. But this one obviously detects waves that are bigger because look at the size of the dumb thing. If you want to know what size of waves something is designed to detect, look at the size of the thing, of the detector. This thing is meters across, maybe 10, 20 meters across. So it's measuring waves that are at least that big. Here is a installation in New Mexico called the Very Large Array. You can't really see how big it is in most of these pictures, unfortunately. This one, I wish they had a really big picture of it. Very large array, New Mexico. Expanded. I'm sorry? Yeah, this has been in a few different movies. Probably the most recent one was Contact with Jodie Foster. So the Very Large Array is a set of 27. I think they've actually added to it recently. I can't remember how many telescopes it has at it, but it has some multiple of 3 number of what we call radio telescopes, which are just these big radar dishes. And you can see that these radar dishes are actually next to railroad tracks. They're railroad tracks that go out for miles in every direction. Right now, all of these things are in close, probably because they need to be maintained. They're probably doing some work on them. When this thing is expanded out, it's huge, miles and miles across. So obviously, this thing is designed to pick up huge electromagnetic waves, which radio waves are. Radar and radio waves are electromagnetic waves, just like red, blue, and green light are electromagnetic waves. One of my favorite ones that unfortunately they're probably going to tear down. Here we go. Is the Arecibo array in Costa Rica. This thing is, I don't know if, see if we can really get a feel for the scope of this thing. So here you can see buildings and cars, and this thing is just monstrous. It is humongous. It's still not as big as the Very Large Array in New Mexico. It's not nearly so big, but for a single dish, it's quite huge. And it's so big that underneath it, that you can actually walk underneath. I mean, they can drive cars underneath this thing. This is what it looks like underneath, a little jungle underneath it. That's been in several movies also. It's been in 2 or 3 James Bond movies. It was also in Contact. Contact was a movie made by, it was a book written by this man here, actually. This guy right here, Carl Sagan. He was an amateur astronomer and a huge proponent of science and education. He died a few years ago. What's that? I can't hear you. Carl Sagan was a great proponent for a lot of great things, for sure. I actually have several of his books. He was a good man for education and science in general. And he wrote some pretty good books. He had a great TV show called Cosmos on PBS for decades. And he was great friends with a lot of great science proponents like Bill Nye and other guys like that. Anyway, so the electromagnetic waves. In physics, we often use the word light for electromagnetic waves, and we use light to describe all kinds of electromagnetic waves, including radio waves and radar waves, and even really, really small waves like X-rays are another kind of light, and gamma rays and other things. But here they show that the speed of light is 1 over the square root of this thing, like I mentioned. I mentioned both the square root and 1 over the square root because I couldn't remember which one it is, but it is 1 over the square root. Another scientist who was able to add some light to this discussion, no pun intended, was a guy named Hertz, who we of course know, Heinrich Hertz. His name is used to describe frequency. And he was able to make the first radio transmitter and the first radio receiver, where he had this this device here, and you can see some of the elements in here that you're familiar with, like a resistor, an inductor, and a capacitor. So this will resonate at a certain frequency, and that frequency will be transmitted through a transformer to increase its voltage. And then that voltage will cause a spark to occur between these 2 points. This is often called a Helmholtz coil, or not a Helmholtz coil, can't remember what it's called. But anyway, what this is in essence on the right side is the transmitting antenna. We don't use a spark anymore to transmit this. But if you separate these two and don't let the spark go, then you can create an antenna that sends out a signal, and you can receive that signal with another antenna and another device that's very similar to this. And what he was able to show is that these accelerating electrons created these electromagnetic waves that were picked up by or detected by this other device, as the electromagnetic waves induced currents in the other device. So it was the first radio transmitters. And this was in the mid to late 1800s. I mean, I'm not sure if you know when the first radios were used, but my goodness, it was not right then. Wasn't too much later, but it was earlier than most people think. So here they show how we can create these electromagnetic waves using an antenna. So this device, this little circle with the little thing in it here shows this is essentially an RLC circuit that creates a resonant frequency back and forth and back and forth. And this resonant frequency drives a current up and down this rod. This rod would be our antenna. Notice that it's not curved anymore, so it creates a spark. So at one point you might have negative charges on the top and positive charges at the bottom, and then at some other point it might reverse. Negative charges on the bottom, positive charges on the top, and that means that the electric field at one point is going up, and at another point it's going down, and at another point it's going up and down, and somewhere in between it's going to hit zero when all the charges are balanced out for a very short moment. But the end result is that you get this electric field up and down. The problem is that we very well know that when you create an electric current in an object, you create a magnetic field that is perpendicular to it, that goes around the wire. So around the antenna, we're going to get magnetic fields that are going side to side. And it's not just going to be in one direction, it's going to be in all kinds of directions. But the end result is that we get a magnetic field that is perpendicular to the electric field. So if the electric field is up and down, the magnetic field will be side to side, coming in and out of the page. And this is what it could look like. Electric field going up, magnetic field coming out. Electric field going down, magnetic field going in, and so on and so forth. Now this is a very nice clean wave, very organized, very symmetrical. Not all electromagnetic waves are this way. But if you can create a wave like this, you could calculate the frequency, you could measure the wavelength and do other things like this, and you could figure out what kind of electromagnetic wave you got. If it's the kind you can see, if it's got a wavelength of like 600 nanometers, you can see that. It'd be like orangish, yellowish. If it was 400 nanometers, you'd have a hard time seeing it. You might see it a little bit, but it would be very ultraviolet. It'd be close. It would be like a whitish blue color that you could barely see, but it would be dangerous for your skin. You could get a sunburn from it. And it turns out there's another interesting relationship between the electric and magnetic fields that are created by a single source. If you take the electric field's magnitude, the strength of the electric field, in other words, the maximum maximum amplitude of the electric field, and divide it by the maximum amplitude of the magnetic field, at any given point in time and space, it will equal the speed of light. Well, that's kind of interesting. That means that the electric field is way bigger than the magnetic field, because the speed of light's a big number. So if the ratio electric to magnetic is a big number, that means the electric field is 300 million times bigger than the magnetic field. So even though there is always a magnetic field with electromagnetic fields, it's very small in comparison to the electric field. And here in this example, they have us calculate that. We have what they want to ask. They want to know what is the maximum strength of the magnetic field. If the electric field strength is 1,000 volts per meter, you rearrange the equation to solve for B. 1,000 divided by 300 million, you get 3.33 times 10 to the minus 6 Tesla. So micro Tesla, very, very small. So if you're going to detect electromagnetic fields, the best way to detect them probably is to detect the electric field. It's a much bigger number. Let's see if this one works. So here is our radio tower, and we're going to create electromagnetic waves by wiggling the electron up and down the antenna. And as those waves go through, they wiggle electrons over here. Right? Now let's create one that makes a little more sense. Because notice that this electron, the electric field, goes the opposite direction of the electron because electrons always move against electric fields. It's positive charges that move with electric fields, right? So there we go. If we increase the amplitude, that's like making the radio station louder. It's like making the sound louder at the other end. If we increase the frequency, it's like changing the channel. If the frequency goes up, move the amplitude down here. So if the frequency goes up, that changes the channel. Frequency goes down, that's 0, that's not going to help us. Very slow frequency. Makes the wavelength longer. So anyway.
So, as far as picking up those waves, like on a smaller radio, that's no problem. You just need the humongous dishes to measure it, right?
Which are you talking about particular waves or just waves in general?
Yeah, like the wave there that was larger than the house that was passing. That house had a radio.
So the antenna, the length of the antenna is what matters. It's the length of the antenna that matters, not. And it depends on what kind of signal you're sending out. There are different kinds of signals that are detected in different dimensions. But for example, AM radio, all you need is a wire. And the length of it determines what you can pick up. You can pick up pretty much any AM signal with a wire. The longer the wire, the better the pickup. If you wrap it in a circle, it makes it even better. With FM radio, you have to have your antenna has to go sideways because it's the frequency that changes, and the length of the antenna determines the size of the wave that you can. So if you're using FM frequency modulation, you have to have a really long antenna depending on what kind of waves you want to pick up. You use a shorter antenna for shorter waves, longer antenna for longer waves. So it depends. You don't need a dish at all for those waves. A dish gives you a two-dimensional signal because it's a two-dimensional object. or three-dimensional, you could think of it as, but, excuse me. If you're just looking for a one-dimensional, if you're just trying to pick up a one-dimensional wave, like a voice transmitting wave, then you don't need a dish. So the reason that they use the dishes is so that they can make images of what's going on with them. They can say this one's coming from this direction, this one's coming from this direction. You have to have a dish to localize. So, in fact, you have to have many dishes to localize. So, more than one. You have to have three, at least. Okay. So, here is the electromagnetic spectrum. A part of it, anyway. Up here, they're showing you wavelength. Down here, they're showing you frequency. And right here, they're showing you what we can see with our eyes. Our eyes are able to detect this little band right in here. The frequency is around just under 10 to the 15 hertz. So that's why we don't use the frequency, because it's just too big of a number to talk about. The wavelengths are somewhere between 400 nanometers and 800 nanometers, somewhere in there. If you make shorter waves than that, then your wavelength decreases, this is decreasing wavelength, and your frequency increases. That's because the speed of light is directly related to the frequency and the wavelength multiplied together. So if your frequency goes up, your wavelength has to go down, because the speed of light stays constant. So as your frequency goes up, your wavelength goes down. So if you have a smaller wave than the one that we can see, which is the purplish, then it gets into what they call the ultraviolet. And the ultraviolet goes down to tens of nanometers or so. Once you get below a single nanometer into the below nanometers are what we call picometers. Then you're into the X-ray range as well. The ultraviolet and the X-rays overlap a little bit. This region in between is called the soft X-ray region. We use soft X-rays to do things like mammograms. The reason they're called soft X-rays is because they can image soft tissue. If you do a mammogram, you're mostly taking imagery of fatty tissue. And you want to be able to distinguish between the fatty tissue and the tumor, which is slightly more dense. So you don't want to use a really, really small X-ray wavelength, because it will just go right through that stuff. You won't see anything. So you use something that's kind of ultraviolet and kind of X-ray. It will go through fat tissue, but it will see it as well. It will make an image of it. And so that's why it's called soft X-rays. And then the hard X-rays out here overlap what we call gamma rays. Hard X-rays right here in the middle are the X-rays that we use to look at bones. So they'll just go right through muscle and fat. You won't see them at all, but it will make an image of the bones. And there are many X-ray machines that you can change so that they are different frequencies, so that you can get different wavelengths, and you can see different things. For example, X-ray machines that do the CAT scans. It depends on what you're looking at with the CAT scan. A CAT scan is an X-ray machine that takes many, many images from different angles and at different depths using different frequencies, and then it combines all those images using a computer to make a three-dimensional image. And that's what CAT scans are. Mostly they're just a big computer. But they change which X-ray they use. And then gamma rays are everything else that's smaller in wavelength than X-rays. And the reason, these rays out here are extremely dangerous. Like if you get out into this region here, these gamma rays can disintegrate anything. Literally, anything. It will disintegrate, it'll break down everything into protons and neutrons and electrons, and it will completely disassemble atoms. It's got so much energy. Extremely dangerous. This is the stuff that comes out of a nuclear bomb when it first goes off. When a nuclear bomb first explodes, the first thing that happens is it vaporizes and disintegrates every single thing around it within a few meters. so that everything near where the bomb was becomes nothing but protons and neutrons and electrons, because there's so much energy. I'm not sure if it's a few meters, it's probably not quite that big. But that happens before any light comes out, before any heat comes out, before any explosion. These things travel at the speed of light, so they are before any kind of visible light comes out. And then everything else happens later. So these are extremely dangerous rays, and they're the kind of rays that you would get exposed to if you're near nuclear power plants, or if you're in a nuclear power plant or a nuclear submarine, if they didn't shield it. These kind of rays can be blocked to a certain extent, as long as they're not too energetic. And they do their best to block them around those things, using lead and other things. If we go the other direction, off the red end of the spectrum, you get into the infrared, which is the kind of light that things that are warm or hot give off. When you make something hot and it's glowing red, but it's not really that red that is like the red of a cherry or the red of a tomato, it's kind of this weird red, that's infrared. And we can see it if it's really, really bright. So if something is really, really hot, we can see it. But if it's not really, really bright, we usually can't see it. All of us in this room are giving off infrared light, but we can't see it because it's not enough to see. But I do have a camera somewhere, maybe we'll get it out tomorrow, that is designed to pick up infrared light. And you can see infrared light through that camera. So if you go further out, you get into the radio wave region, which starts with microwaves. So the first radio waves, we call them microwaves. And right here, somewhere in the middle, there's a particular frequency of microwave that is used in microwave ovens. It's used specifically because it makes water vibrate. It resonates with water. So if you have that particular frequency inside of a microwave oven going back and forth through the oven, and something in the oven that has water in it, the water will vibrate with that frequency and it will warm up the food that the water is in. That's how microwave ovens work, essentially. And then you have TV and FM radio, which are at the far end of microwaves. We're getting longer in wavelength as we go out this way. So TV and FM radio are longer than the microwave that we use to heat up water. Can you guess about how long the wavelength is, the one that heats up water, from the size of a microwave oven? What's the smallest microwave oven you've ever seen? This big-ish? Yeah, so you can probably guess about the size of the microwave that is used to heat up water. It's probably something like that, within an order of magnitude. Might be 10 times bigger or 10 times smaller, but probably 10 times smaller. TV and FM radio are starting to get much longer. Let's see what length we're at. So in here, in the microwaves, we're in the centimeter range, all the way up to the tens of centimeters, even hundreds of centimeters possibly. But then out here, we're getting into the meter range, and even out into the tens of meters or even hundreds of meters range. AM radio is in the hundreds of meters range. And then radio waves go way out to the millions of meters range. They can get much, much longer.
Is there like a reason why it's like classified as different, or is it just like the waves are different, or is it just kind of like broad?
Why they're classified AM and FM and all that?
Is it like just because of frequency and wavelength?
It's because they're more suited to this kind of thing. So AM radio was designed to carry voice, but not music. So talking voice. This was the first kind of radio that was used originally, and it was just for people to talk to each other, send out AM radio waves. And they did send out music on it originally. You know, there are music broadcasts that go back to 100 years, more than 100 years ago. But they were not in stereo, because AM radio does not allow for you to do anything in stereo. So it's completely monotone, not monotone, mono, what do they call it? But anyway, mono radio. You couldn't hear the effects of a stereophonic effects. And the good thing about AM radio is that it can travel long distances. So because the longer the wavelength, the longer it can travel, turns out. So it can travel very long distances. I can pick up a radio station in San Francisco in North Platte at night. So it's that's one great advantage. One of the disadvantages to AM radio is it's hugely affected by other waves that we create in the world today. 100 years ago, we didn't create so many waves in the world. Now we create a lot more. And AM radio waves are hugely affected by, for example, the waves that are going in the towers for electrical waves. If you're listening for electrical power, if you're listening to an AM radio station and you're traveling underneath high power transmission lines, it will completely mess up your radio station because they're similar frequencies and they overlap each other. So it can really mess up your AM radio station. So that's one of the disadvantages to AM radio. The fact that it's not stereophonic and also that it's messed with, it can be easily messed with. If you go to higher frequencies, it turns out it's more difficult to mess with higher frequencies. Higher frequencies tend to be a little more stable, but they travel shorter distances. Cell phones work even higher frequency than FM radio. They work up in here, in this range. But you have to have cell phone towers everywhere because it only travels very short distances. When you make a cell phone call, it only travels through the air as an electromagnetic wave until it hits a tower. Once it hits a tower, it goes to a landline and it travels by land. Because if you travel tower to tower to tower to tower, you'd never make a connection with a cell phone. So it never does that. It goes from your phone to the closest tower, to a landline, to the tower closest to the person you're calling, up, out into the air to their cell phone. Which is why you get that huge delay with cell phones. Which is why they switched everything to digital cell phones. It used to be that you had analog cell phones and you had much better sound quality if you had a good connection. If you had a bad connection, it was terrible. And if you had a bad connection, the delay was so bad, so long. So they switched to digital, which they can send the digital signal much quicker, so they would cut back on that delay. But the delay is still really big, and it always will be, because it's essentially determined by the speed of light. It goes through the air at the speed of light, down to the landline. On the landline, it travels at the speed of light, because it usually is traveling through a fiber, which is pretty close to the speed of light. But it still has a distance to travel, so it takes time and then it has to come back. So anyway, FM radio works differently. It uses sidebands and it can do stereophonic sound and higher frequency. You can get better resolution, so you get better sound overall. But it travels shorter distances. So you have to have bigger towers, higher energy towers. You have to be closer to them. Submarines use an interesting wave that's way out here called extremely low frequency waves. It's a really, really long wavelength. And the reason that they use it is because when they're deep under the water, the only thing that can travel from the air to the water, through the water, is a really long sound, a really long electromagnetic wave. So they have to use that low frequency to receive their signals. There's another way that they can do it as well. They can trail an antenna behind them that is like 2 miles long. The antenna is made of glass, so it's not visible on radar, and it can pick up radio waves. But since it's a very, very long antenna, it picks up very, very long waves once again. So their antennas, the submarines, when they're underwater, and they're underwater almost the whole time they're away from their dock. They usually stay underwater for 2 months at a time, at least. But while they're underwater, their signals are coming on such a low frequency wave that they may only get one letter every 10, 20, 30 seconds of one letter of the signal. So it might take them 10 minutes to get a short message to the submarine. So everything is done in code. You have the signals that come through, every letter means a word. Everything, every little thing means a word. And it comes through in very, very, very interesting shorthand. You don't get a letter from home this way when you're on a subway. You don't get letters from home at all when you're on a subway. No communication with the outside world. This is what amplitude modulated radio looks like, where they change the amplitude of the signal. This is AM radio. The sound is this wave that's inside of the black wave. So that's the actual sound. Sorry, the sound is the black wave. The carrier wave is the one that's inside of it. So you're changing the size of the wave to indicate the voices that are on this, or whatever sound it's carrying. In FM radio, it's frequency modulation. So here's the wave that you start with. Here's the audio signal. When you combine them, it makes different frequencies. So the frequencies go back and forth. This is not exactly how it works, but it's pretty close to explaining it. So now they want us to calculate some wavelengths when they give us frequencies, and frequencies when they give us wavelengths. You just use this equation. It's pretty simple. Solve it for the wavelength, plug in the frequency, solve it for the frequency, plug in the wavelength. I'm not going to go into details with that. Here's another equation where they want us to calculate let's see. We're going to calculate how much energy is absorbed when they use ultraviolet light on the cornea of a patient. So here what they're doing is vision correction. This is LASIK surgery, essentially. So in LASIK surgery, what they do is your cornea has this shape to it. The cornea is kind of like part of the lensing system of your eye. It's not the actual lens of your eye, but it is part of the lensing system of your eye. And what they do is they zap it with a laser, and they essentially burn off, evaporate a layer of the cornea to shape it a different shape than it was before. And hopefully the new shape will focus the light differently so that you can see better. And that's the idea behind LASIK eye surgery. The problem with LASIK eye surgery is that if you shave off too much of the cornea can collapse because the strength of the cornea is determined by its thickness. And the cornea gets bent and twisted and squished a lot by your eyeball, the muscles in your eye, which gives you color, that gives you color to your eye. Those are muscles. They actually squeeze the cornea and relax the cornea, stretch it and squeeze it so that you can focus on different things. When you're focusing on things that are close, your eye gets squeezed to a point that it is, let's see if I'm thinking this right. I think it squeezes it. It squeezes it so that it can focus that very close light onto the retina. When it's far away, it relaxes it and stretches it out. But that squeezing and stretching can actually cause the cornea to collapse. Eventually, for all people, it collapses eventually, or it starts to weaken, and you lose your eyesight, and you start to need glasses or bifocals or trifocals. But if you weaken your eye using LASIK surgery, it can accelerate this effect. And this is something that the FDA kind of ignored because there's so much money in LASIK surgery. LASIK surgery requires no skill or ability and hardly requires any training. So the people that do LASIK surgery, anyone can do it. It doesn't require a great surgeon. In fact, they don't even have to be surgeons at all. They can just be an eye doctor trained in LASIK surgery. And it used to be before that you actually had to be an actual medical surgeon to do eye surgery. So you had to go through medical school, and then you had to go through medical school again to become a surgeon. And then you had to learn eye surgery, so you were in school for at least 15 years before you started eye surgery. So you had a lot of experience, a lot of skill, and you, instead of shaving layers off the eye, you would cut little slits in the eye, and those would reshape the eye. The eye heals very well. And when it heals, it actually heals stronger than it was before. So the old style of surgery, radial keratotomy, which is hardly done anymore, would make your eyes stronger and you could see. The only side effect being that some people would get scars that were very, very small, but at night you could sometimes get some refraction off those scars. But for most people, there was no side effect to it. Took longer to heal. Took about a week to heal instead of 2 days. But it was a much better surgery, but we don't do it anymore. Not in the United States, not much anymore. Because LASIK surgery is easier, simpler, requires no skill or training, and it's money. It's all about money. How much does LASIK cost? Anybody know? A couple grand per eye. Yeah. And it takes an hour. It takes them an hour. They're getting $2,000 per hour. That's ridiculous.
Some people don't, or some people have to go back in.
Oh, absolutely. And some people lose their sight permanently with LASIK, and they're just realizing this. They knew that this would happen, but the guy, I actually met one of the doctors, I knew him, who actually invented LASIK surgery, and they were inventing it not for eyeballs, they were inventing it for surgery of the sinuses. But they quickly realized it could be used for eyes, and two of the doctors that were working on the project immediately starting to use it for eyes. He refused because he said 20 years after the first LASIK surgeries were made, people are going to start losing their vision because of LASIK surgery. And it won't be everybody, but there will be a high percentage of people who had LASIK surgery that was pretty extreme because they wanted to correct vision that was really bad and have 20/20 and not have to wear glasses or contacts. And their corneas are going to collapse from all the use. And there's no replacement for that. There's no fix for that. I mean, you can do a cornea replacement, but you have to have somebody that's willing to lose an eye or died and doesn't need their eye, right? But it's unfortunate, but the FDA does that stuff all the time. They don't look into the science of it. They look at the money more than the science. Drugs are approved all the time that are totally dangerous. And they know they're dangerous, but they're willing to take that chance because of the money. Think the FDA doesn't care about money? Think again.
I remember a video of a guy who, on stage, down a whole bottle of sleeping pills, everybody was gasping, and he's like, "Don't worry, they're absolutely worthless." And that's what I understand that the FDA does all the time. It either doesn't work or it works dangerously.
In this problem, what they're trying to do is show us that the energy that vaporizes this material in your eye is related to thermodynamics, but also related to the energy in the light. So they're using thermodynamics equations to change the temperature and then to vaporize the material in your cornea. So here's the change in temperature. Remember that equation, the specific heat equation? And then here's the latent heat of vaporization of the material. And so you add those two equations together to get the total amount of energy required to vaporize this part of the eye. You also have to know the mass of the material, so they calculate the mass. And then they add those two together, and the total amount of energy that you need is 382 times 10 to the minus 9 kilojoules. It's not that much, turns out. Doesn't take that much. Here they talk about ozone. So ultraviolet light is high energy light. And what it can do is ultraviolet light, as it comes into the earth, it encounters oxygen in the atmosphere, in the upper atmosphere. The oxygen absorbs the energy from the ultraviolet light. It absorbs the ultraviolet light. But it creates an interesting situation that allows oxygen molecules, which are usually two oxygens, to be ionized and attract another oxygen molecule, so that they create an oxygen molecule with three oxygens. So that is what we call ozone. And the ozone is quite important. This creation of ozone, because of the ultraviolet hitting our outer atmosphere, actually protects us from ultraviolet light. If that ozone wasn't being created out there, if we had less oxygen in our atmosphere, for example, then ultraviolet light wouldn't be absorbed and would come down to the earth and would kill everything. Ultraviolet light is very good at killing things. So the ozone layer actually helps protect us. There is a hole in the ozone layer at the South Pole and at the North Pole. But it is probably because those two poles don't receive as much ultraviolet light. The ultraviolet light hitting at the poles is just not as much because the poles are not facing the sun. Right? So when the ozone layer was first discovered, everybody was freaking out. I actually met the scientist who discovered the hole as well. I knew her as well. And she said, actually, we kind of figured it was natural. We figured it had always been there. But everybody started freaking out. And they started blaming the use of CFCs, spray bottles. And they're talking about it here. It's so lame. The hole in the ozone layer is natural because light is not hitting there. The ultraviolet light's not hitting there as much. So the ozone layer is naturally going to be much thinner or even non-existent. Why would there be a ozone concentration over the South Pole when nobody's spraying hairspray there? There's nobody in Antarctica with hairspray or spray paint. It's such a ridiculous thing. Like my addressing of these issues. Anyway, how are X-rays created? I actually have an X-ray tube right here in my drawer. A couple of them actually. These are X-ray tubes that were made by the company that I used to work for. Called Mox Tech. There are different ones. Let's take a look at them here. These are very small X-ray tubes. Most X-ray tubes are like the size of your arm or bigger. These are very small X-ray tubes that were designed to go on the Mars rovers. They needed to be small because of the fact that the Mars rover is small and you only have a certain amount of space to put things on it. But they also needed to be small so that they would use a small amount of energy because the Mars rover only had a certain amount of energy to be used. This one right here is what we call a copper target, and it has its shielding removed. We removed the shielding to do some testing. But this end of it is a piece of copper. There's a window on the front that you can't see through, even though it's called a window, because it's a window made of beryllium. Visible light will not go through this window, but X-rays will go right through it. It's made of beryllium. And then at the other end of this thing, where you can't see it because it's covered in this epoxy, can't see it in these ones either, but at the other end of this is essentially a little light bulb. Excuse me. This is what it looks like inside if you took all the epoxy off. This end is where you have what is called the target. This is what is called a window target. So the window is made of beryllium, but it's coated in silver, and the silver is the target. This end is connected to a little light bulb inside of this tube here. This is a ceramic tube. And what we would do is we would put a huge voltage between the two ends of this, 40 kilovolts, 40,000 volts between the two ends. And then we would put a little current through the little light bulb and create 3 electrons inside the tube. The tube in the middle is in vacuum, so there's no air or anything in between these two metal parts. And we would light up this little light bulb in there, and electrons would escape from the light bulb. It's like a little filament that would get hot. And electrons would boil off. And as the electrons boiled off, they would accelerate from one side to the other. 40 kilovolts of acceleration, 40 kilovolts of potential difference. So they would accelerate. And by the time they hit the target, they would have 40 kilo electron volts of energy. When they got to the other side, they would hit the metal. And the metal would absorb all of that energy of those electrons. And as it absorbed that energy, the electrons in the metal, in the target, would jump up in their energy levels in the atoms. They would jump up really high, and then they would fall down, and we'd get this huge energy change, this huge energy difference. and it releases very high energy light, which is essentially X-rays. So that's how X-ray tubes work. Let's look at a so here's another good image of this where you have your filament that's shooting off the electrons. You have a voltage between here and here. They have these very close together. Sometimes they are pretty close together. This is encapsulated with glass and a vacuum inside. Has a copper target. As the electrons hit the copper, the X-rays come out the side in this case. In ours, they came out the end. Either way. It works. So, how do you calculate the energy in electromagnetic waves? In general, excuse me, in general, the energy in a wave is determined by its amplitude, or the height of the waviness of a wave. But you also have to consider how often the wave is hitting the object that is absorbing the energy or encountering the object. So the frequency matters as well. And it's particularly true in light waves because the frequency doesn't affect the speed of the wave. The frequency of a wave in water can affect the speed of the wave in water. But the frequency of the wave in light does not affect the speed of the wave in light. It's always going the same speed, so if you increase the frequency, you're going to get much more energy. So it turns out that you have two ways to talk about the energy of light waves. You can talk about the energy, the intensity, or this would be like the brightness of the wave. The intensity, on average, is proportional to the electric field squared. It's also proportional to the magnetic field squared. It's a different equation either way. In this one, you've got epsilon naught in it and speed of light. In this one, you're dividing by mu naught and you're multiplying by speed of light. Either way, you get the same solution. But you can also just combine these two and get this equation. E naught, B naught, maximum amplitudes divided by 2 mu naught. So that will calculate the brightness of the wave or the intensity of the wave, which is part of the energy. So let's talk about the energy of a microwave. We have a 1,000 kilowatt or 1,000 watt microwave, 1 kilowatt microwave. And we're putting all that energy into a space that's 30 centimeters by 40 centimeters, which is about the size of a small microwave. Maybe a big microwave. You want to know what is the intensity, what's the peak electric field and the peak magnetic field? Well, the intensity can also be calculated from the power. It's just power versus area, the power divided by area. That's the definition of intensity. So we go ahead and calculate the intensity first. The peak intensity is going to be twice the average intensity. That's something we learned when we first talked about waves. So our peak intensity, I0, is 1.67 times 10 to the 4. You can calculate your electric field by calculating by rearranging your equation for the average intensity. And you can do the same thing for magnetic field. Or you can use this equation, which is what they used. You could use this equation, or this equation, or this equation, or you can use the one that relates the two intensities of the fields, which is just, excuse me, which was just C equals electric field over magnetic field. Just rearrange it and solve for the magnetic field. Anyway, it works. It's not terribly difficult math we're doing in this chapter. So, yet. What section are we in here? Ah, we're done.
Can I go back to,
One we just looked at?
yeah.
We can't be done.
Fairly short chapter.
You must have pushed the wrong button. Oh, I already. That's okay. Okay, let's see, what are we doing?
For the solution to part B, what is that?
This equation?
Yeah.
That is an equation that we saw way back here in
Right above it, part B.
this one.
That one.
This equation came from right here. It's this equation solved for the electric field. I wish they numbered the equations in this book, but they don't. Did you see which equation it was?
That one.
Yeah,
Okay.
they just solved it for the electric field.
And you end up with it raised to half.
Yep, that's the square root.
Okay.
So since we finished this one so quickly, we're going to move on to chapter 25 by doing a geometric optics lab tomorrow and Thursday. We're just going to do a whole bunch of optics in class. So we'll have a homework assignment for chapter 24. It won't be terribly difficult. But now it's time to do some geometric optics. So far we've been mostly talking about light mathematically, but now let's talk about it geometrically. What does it mean when light starts to bend through things? This is much more interesting than what we've been talking about today. It's a great mirror from one of the space telescopes that they're putting in space. I don't know which one. It's kind of cool looking. Nice little rainbow over Montevideo, Uruguay. So what are geometric optics? We're going to start this chapter really quick. We'll essentially have 2 homework assignments this week, but neither one of them will be terribly mathematically challenging. And we will do lots of hands-on work with optics. So what is a geometric optic? A geometric optic is something that uses the shape of a material to manipulate light somehow. And as we talk about light in this chapter, we're not going to talk about it as a wave anymore so much, as we're going to talk about it as a ray. So in other words, the ray of light shows the direction of the travel of the wave of light. So if the wave of light is traveling in some direction, you can draw an arrow in that direction, and that's the ray of the light. And we deal with light rays a lot in geometric optics. So here is one of the simplest geometric optics problems there is. The mirror, right? So here's a quiz for the day. Get out a piece of paper. from this picture, can you determine how tall a full-length mirror has to be for a man who is 2 meters tall? That's a tall person, by the way. We have a couple basketball players that are over 2 meters tall here, but not many other people. Former student of mine who goes to school here still is over 2 meters tall. Nobody in this room is over 2 meters tall. You told me how tall is. How tall are you, Billy? 6'2", not quite 2 meters. Still a few inches short. So, the question is, how tall does a full-length mirror have to be for a man who's 2 meters tall? Full length meaning he should be able to see the top of his head and the bottom of his feet. What is the shortest full-length mirror he can use for a 2 meter tall person? You should be able to use this picture to determine that this picture is physically representative of what happens with rays of light. It does show us precisely what happens.
2 meter tall person?
2 meter tall person. Any more time? If you now, I think you can put your name on it. And the height of a full-length mirror for a 2 meter person. The minimum height. What is the shortest height a mirror can be? For him to see the bottom of his feet, top of his head. And this image is representative of what will happen with the light rays. So you can use this image to determine the answer to this problem. Today is the 28th. February. Got it? Okay, who's got an answer for you? What do you think? What's that? A little bit more than a meter? Anyone else?
It's just about around half this height.
A little bit less.
A little bit less than a meter? Half a cent. Good. It is actually, let's take a look at the solution here. For the 1 point, this person is 1.65, and it says that it has to be 0.890, or precisely 1/2. That's not precisely 1/2. Oh, Yeah, his eyes are this way and his head is 0.13 meter higher. So his height is actually 1.8-ish. Yeah. So it's close to 1.8. But it is half, actually. You can get away with half. Most people would do a little bit more than half, just so they can see the floor beneath their shoes. But a full-length mirror does not have to be full length at all. Half length is perfectly fine. And you can see that with full-length mirrors. Anybody have a full-length mirror in their house? Does it go all the way to the floor? What? Goes to the bottom of the door, which is not all the way to the floor. Does it need to go all the way to the floor? No. In fact, they're not even made that long. You can't buy a 6-foot tall mirror. You don't make it. The tallest one that I've ever seen was 4 feet long. There's no way. You don't need 4 feet is way more than enough. It's enough for an 8-foot tall person to see their whole person, right? So many of them are often just 3 feet, 3.5 feet. You know? This is what we call the law of reflection. Rays of light bounce off of mirrored surfaces at the same angle that they encounter the surface. We measure the angle from the normal, not from the surface. And it doesn't even matter if the surface is flat, it turns out. Even if the surface is curved, it will bounce off at the same angle that it encounters. The incident angle and the reflected angle will be the same. And this is how we measure it. It's from that perpendicular to the surface, we call that the normal to the surface. If we measure it from the surface itself, then this law would not necessarily work out so well if it was a curved surface. So we don't measure from the surface, we measure from the normal, and this law is always true. The incident angle is equal to the reflected angle always. One place where this doesn't work out so well is on surfaces that are not smooth and reflective. What we call diffusive surfaces, rough surfaces. And that's like, walls. We don't want reflections off of walls. So what do we do to walls? If you just take a wall and make it very smooth and paint it white with really glossy paint, it will be reflective. You get all these reflections from the lights in the road. But if you put bumps on it, if you look closely, there are bumps on this one. Not really big bumps. How do they get the bumps on the wall? Well, in this particular case, they just use a really big roller or a sprayer that sprays the bumps on the wall. Right? In some cases, they put really huge bumps on the wall, in some houses, in some buildings. But that diffuses the light because the light will reflect off, and the law of reflection will be true, but every ray of light that hits will be at a different surface that's angled at a different angle. So it'll just bounce the light all kinds of weird directions. Of course, the law of reflection can be compounded. So you can hit one mirror, bounce off, and hit another mirror. And hit another mirror, another mirror. But the law of reflection is always true. Angle of incidence equals angle of reflection every time. Now, what happens if you don't reflect off of something? What if you go through it? Some of you have probably seen this effect, where you look at a fish tank from the corner, and you see multiples of things. The reason for this is what we call refraction. This actually happens in space as well. Looking out into space is kind of like looking at a fish tank, where instead of having water being the thing that bends light through space, it's actually gravity. There are certain stars out there that we can see 2 of, and they're the exact same star. It's obvious that they're the exact same star. They blink at the exact same rate, they have the exact same spectrum of light. Everything about them is exactly the same. And for some reason, we're seeing 2 of them. And that's actually how the first black holes were discovered. Black holes bend light, like water bends light. So it's kind of interesting. But in this case, we're looking at the corner of a fish tank, and what we see is two fish. But what there is actually in the tank is one fish, right behind the corner. And what's going on is that the light that is traveling from the fish, as the fish is giving off some light, its electrons are vibrating, creating these light rays that come out, is going outward and hitting this glass at this surface here. And as it goes from water to air, it turns. Why would it do that? Why would light turn as it goes from water to air? How many of you have ever driven an off-road vehicle? Anyone? Couple of you? Four-wheeler? So what happens when you go from your pavement or your hard-packed road to like sand or gravel? What happens to the steering as you go from that really good surface to that mushy surface? It slows down, right? What happens if you're going off at an angle? So you're not just pulling into it straight, you're like pulling off it into an angle, like on the side of the road or something like that. You start drifting which direction? Into the surface, into the gravel, or out of the gravel? You get pulled into the gravel or you get pushed out of it? How many of you have hit rumble bars on the road before? The rumble bars on the side? Do you have to force your car out of those, or does your car get pulled into them? Or that's the same thing. Does your car get pushed away from those automatically, or do you have to force your car away from them by hand?
It's kind of pushed away from them.
Not in my experience. So you drive along and it pulls me in, and I have to force it out. If I did nothing, if I let go of the steering wheel and hit those rumble bars, my car would go off the road. Isn't that what happens with yours? You have to like force it off because it goes and it gets louder because you're getting pulled more into it, right? It doesn't just go beep and stop. It doesn't just push out. Because if it did, it would just push you back on the road, which would be bad if you were falling asleep, right?
I guess I'm just a little more faster to pull myself back on.
But you are pulling yourself out, and that's the point. You just don't realize you are, right? You're actually pulling on that wheel. You're like, oh, I want to get out of this, but you have to steer out of it. That's because they're pulling you in, and they're designed that way on purpose. How many of you have been to Wyoming? Where do they put those rumble bars? And in the middle. Is that smart? If you're falling asleep, do you want to be pulled into the middle of a two-lane highway? No. I think people that design the roads in Wyoming are idiots. I hope that none of you are related to the engineers who design those roads, but I think they're absolute idiots. You have and they're 85-mile-an-hour roads. 85 miles an hour going both ways, and there are rumble bars in the middle. If one person gets in those rumble bars, they're pulled to the other side of the road. I watched a head-on accident happen. I watched it happen. A guy fell asleep at the wheel and got caught on those rumble bars that pulled him to the other side of the road, right into head-on traffic. I mean, it would have killed him.
Why would they be sitting in the middle of the road?
Because they're idiots.
Do they think people...
They think it's going to wake somebody up, but what it does, it pulls you into oncoming traffic. Or shoot. That's what it opens up.
Someone freak out when after they wake up being pulled into the lane?
Well, yeah, of course it is.
More likely.
Yeah, of course. It's stupid. That's what it is. You want it to pull them off the road. It should only be on the right side of the road if you're on a two-lane road. If you're on a road that is only going one direction, a freeway, if you're on I-80, it doesn't matter what side of the road you're on. You're going to be pulled into the ditch. And that's fine. It's safe, right? For everybody else. It might not be you much good, but it's safe for everybody else. But it's the stupidest thing I ever saw. And I watched a head-on collision happen at 85 miles an hour. And I had to stop, and I had to administer first aid to somebody that could have died that day. Three people that could have died that day. Bleeding with blood everywhere, and head injuries, and arm injuries, and all kinds of things. It was really bad. But it was just a stupid design. I'm still haven't written a letter to Wyoming on this shit. So you guys are stupid. You didn't be stupid. I think you've been on Highway 30 recently, and that's what brought it back to my head. I'm thinking, people are stupid. I think they have done it, but not in just one place, like on Hershey or something. Was it on Liquid? I can't remember. I heard about it, but I didn't see it. So. Anyway, the point is that it's stupid to put those in the middle of the road. It's stupid. And because it pulls you in, now why does it pull you in? Here's the big question today. What is causing that pulling you in? What are those rumble bars? What does the sand or the gravel do to one side of the vehicle that it's not doing to the other side of the vehicle? It adds friction, which does what to that side? Slows it down. So one side is slowing down while the other one keeps going. That turns things, doesn't it? So it's going to turn you towards the rumble bars, towards the sand, towards the gravel. You ever wonder why they have those huge gravel pits on the sides of freeways for semis? You've seen those in the mountains at all? Oh, it's because they want the semi to be pulled into that pit. All the semi has to do is get one wheel in there, and they're off the highway, and they're safe. And everyone else is safe. And they're deep gravel pits. Yeah, in case they use their air brakes. This is the same thing that's going on. As the light is traveling through the water, it travels slower through water. Light travels slower through everything than when it's traveling through a vacuum. So anytime it encounters anything other than vacuum, it slows down. But the light wave has width to it. The ray is not just a single arrow, it actually has width to it. So as this light ray comes in and encounters, let's say that this is the edge of my fish tank. As this light ray comes in and encounters the edge of this fish tank, the right side of the ray hits it first. And it's going to slow down. And the left side is going to increase in speed, or it's going to stay going at the same speed. So it's going to turn this way, right? Until this one hits the fish tank, and then it's going to slow down, and then I'll be going this way instead of that. It turns, right? If I'm coming out of the fish tank, I'm going slow. So here I am, I'm just moving slow. And then I come out of the fish tank, and in this case, my left wheel hits, or my left side of my right hits the air first, and so it goes faster. Then it speeds up, and this one's still going slow while it's going through the fish tank until I get to here, and this one now speeds up. And I go off this. This is what we call refraction. Happens with all waves, it happens with all things that move, in fact. Anything that moves is moving with a speed according to its environment. And when you change environments, that speed can change and you can get refraction. So this bending of light we call refraction, and there's a law for this as well. Determined by the speed of light, which they're going to talk about here for a little bit, which was measured using this experiment. This is an interesting experiment. What you do is you take a light source and you shine it on a mirror that's spinning really, really fast. And then you send the reflection of that light way out to another mirror and then back to hit this revolving mirror. And since you know how fast this mirror is spinning, you can actually calculate how long it took for the light to go out and back this super long distance. They used 35 kilometers when they did this. It's a long distance. And they calculated the speed of light. We'll calculate it in a couple of different ways. But it's due to the speed of light, and the speed of light is directly related to the material that it's in. And if you want to know the speed of light in a particular material, you have to know something about the material. And essentially we just measure it, and we measure and write these things down. And we call it the ratio between the speed of light in vacuum, which is C, which is this number here, and the speed of light in any given material, V, is called the index of refraction. And it tells you how much something will bend. If this number is bigger, the light will bend more if it goes from vacuum to the material, or from the material to the vacuum. If this number is less, it will bend less. All indices of refraction are 1 or greater. So the index of refraction for vacuum is 1. For air, it's just a little bit more than 1. Carbon dioxide a little bit more, hydrogen a little bit more. Oxygen, most gases are 1.00 something. But liquids start to be a lot more. Benzene is 1.5, carbon disulfide 1.6, ethanol 1.36. They start to be a little bit more. Solids start to be even more. Diamond refracts light extremely well, 2.419. When light goes into diamond, it turns it so much that it can actually get captured a little bit. So that the light bounces around inside the diamond quite a bit before it comes out of it. Does it make sense that diamonds look different than other things? Because they have a lot of light, and they're cut in specific ways so that the light going in from any direction will be captured, but it will only go out the top. Because diamonds are designed that way. They're designed so that they capture light coming from every direction, and the light bounces around inside the diamond for a little bit, and then it all comes out the top and makes it all sparkly. That's what you want coming out of a diamond. So diamonds are great. Glass, not so much. 1.5. It's more like water or glycerin or something. Zircon, 1.9. Guess what we make fake diamonds out of? It's much closer to diamond than water. We make it out of zircon, which is what they call cubic zirconium. Cubic zirconium is just a type of crystal made of zircon.
So if you cut a piece of glass, kind of like a diamond would react the same?
No, because it doesn't bend the light like glass. And that's like diamonds. That's exactly why it's so easy to spot fake jewelry with glass. Because it looks very dull. It's clear, but it's very dull. Diamonds are nothing like clear. When you look at a really good diamond, it doesn't look clear at all. It looks white with light. I mean, there's so much light coming out of it, it looks white. So it's very easy to tell between glass and so that's easy to tell between zircon and diamonds. Cubic zirconium almost refracts as well as diamond. So it's much more difficult to tell.
So it's one part material and one part shape.
For that particular effect, yes. And we'll learn more about that effect, which is called internal reflection. We'll learn more about that here in a bit. But let's calculate the speed of light in zircon. The index of refraction of zircon is 1.923. That's this bottom number. And we're putting the speed of light in the top because we solved this for the speed of light in zircon. Turns out to be 1.56 times 10 to the 8, which is half the speed of light in vacuum. The speed of light in vacuum is 2.99 times 10 to the 8, which is 1.56. So it's a little bit more than half the speed of light in vacuum. Here they show the law of refraction with a lawnmower, very similar to our four-wheeler example. But the law of refraction comes down to a mathematical law called Snell's law, where the relationship between the incoming ray of light and the outgoing ray of light are determined by these, by the signs of the angles and the indexes of refraction of the materials. So if N1 is the first material that you're in, and theta 1 is the first angle that you hit the boundary between two materials with, then that the N1 times sine theta 1 has to equal the outgoing material and the outgoing angle times the sine of the outgoing angle. Again, the angles are always going to be measured from the normal. In this case, from the normal between the boundary of the surfaces, or the boundary of the materials. So you have one material, in this case, concrete, and the other material is grass. These aren't really optical materials, but we're using the lawnmower example. And this dotted line shows that normal that we're going to measure the angles from. Theta 1 is measured up here, theta 2 is measured down here. If we're looking at actual optics, it would look like this, where here's air, here is water, the boundary between the two, and here's the dotted line where we measure the angles from to these different incident and refracted angles. So here, they're going to do some calculations of these things. I'm going to stop at this point since we're a little over time. But we will pick this up again, and tomorrow, actually, you will learn more about this, and you will calculate more with this in the lab. So I will post the homework here as soon as possible.